Good evening, everybody. It's 9 p.m. on Tuesday, March 24th. We've got a very loud dog in the background, and this is Nighttime Mathematics Radio. Format of the show is always the same. Just tweet on over to @NightMathRadio and ask your math questions. We'll try to answer them live here on the air. So for the first few minutes, as always, let's listen to some of Apple's lamest beats and wait for the math to roll on in. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, Twitter's a little quiet tonight, so let's take a little break and see what we can talk about. Let's see what Twitter's got in store for us here. Pretty quiet night for the night. Got very little going on. Will anyone save us from the quiet on Twitter? Let's see. Once again, this is Nighttime Mathematics Radio. If anyone has any math questions, feel free to tweet them to @NightMathRadio on Twitter. I'll try to answer them right here on the air. Let's take 2 more minutes to see if anything develops. Welcome back, everybody. Let's take a look at a problem that's actually, in some sense, a related rates problem. This is a basic related rates problem, so let's take a look. 1 second. Pull up my notepad here. The problem here is called, this is a problem from an older edition of Thomas's Calculus Early Transcendentals. It's the problem called a balloon and a bicycle. The problem looks like this. You've got a balloon that's rising vertically above a level straight road at a constant rate of 1 foot per second. So here's a little hot air balloon. It's going up at 1 foot per second. Just when the balloon is 65 feet above the ground, a bicycle moving at a constant rate of 70 feet per second passes under it. Little guy on a bicycle. So the question is, how fast is the distance s of t? And to go to a later point, this thing gets higher. So this is, we'll call the height of the balloon y of t. Call the horizontal position of the bicyclist x of t. And the question is, if the bicyclist is later over here, what's this distance s of t? And how fast is it changing? So how fast is the distance s of t between the bicycle and balloon increasing 3 seconds later? So 3 seconds after the bicyclist gets under the bridge. Well, we need functions for x of t and y of t first. And that's relatively easy, because we know what's happening at time 0. At time 0, we'll call time 0 the time when the bicyclist is directly under the balloon. Y of t is equal to 65 feet. And remember, it's increasing at 1 feet per second, so it goes up by 1 foot per second times t. And you can tell I originally trained in the sciences, so I have a bad habit of writing units on absolutely everything. So that's 1 foot per second times t. The bicyclist's position starts at 0, because he starts directly under the balloon. We'll call this 0. And it increases 17 feet per second. So it increases at 17 feet per second times t. And there's no intercept here, right? Because when t is 0, x is 0. He's directly under the balloon. So the question here is, what is, given those two things, what is ds dt evaluated at 3t equals 3 seconds? Well, what's s? S of t is this is just a right triangle. So s of t is the square root of x squared plus y squared. Both functions of t, so x of t squared and y of t squared. So ds dt is equal to 1 over 2, the square root, just use chain rule like always, 1 over 2 times the square root of x squared plus y squared, times, now because chain rule, you now have to take the derivative of what's inside, 2x dx dt plus 2y dy dt. And the cool thing is, at t equals 3 seconds, we know all of those things. We have formulas for x of t and y of t up here, so x of 3 seconds is 17 feet per second times 3 seconds. The seconds cancel, leaving us with feet, which is good. Leaving us with 51 feet. So the bicyclist has gone 51 feet out because the bicyclist is zipping along. Meanwhile, the balloon is sort of pokily moving upward. So y of 3 seconds is 65 feet plus 1 foot per second times 3 seconds. So that cancels, gives you 3 feet. So it's at 68 feet up. So we know x, we know y, we know dx dt. Why? Because we can take a derivative right up here. dx dt is, to no one's great surprise, 17 feet per second. Remember, they told us the bicycle's speed and it's constant. So, and the derivative of a position function like this is a velocity. So if the bicyclist is moving at 17 feet per second, to no great surprise, dxdt is 17 feet per second. And by a similar logic, dy dt is 1 foot per second. Again, both speeds are constant here, so this is all very easy. Then we just plug these things into our formula. 1 over 2 times the square root of 51 feet quantity squared plus 68 feet quantity squared times 2 times 51 feet, I should say, times 17 feet per second plus 2 times 68 feet times 1 foot per second. And that's our answer. We got to clean this up a little bit. The 2 cancels with the 1/2 in both 2's. Could have done that even before we plugged numbers in, and we certainly should have done. That's okay. So the numerator here is 51 feet per second times 17. And this is a good point to pull our calculator out. This is also a good time to guess. How nice were the authors of the calculus book being? Because if they were being really nice, 51 and 68 are part of a Pythagorean triple. And I don't know that yet. Let's take a look. 51 squared plus 68 squared equals 7225 square feet. Now we have to square root that. 85, they were feeling nice. As you work through some calc books, you begin to learn more and more Pythagorean triples just because the book's authors are feeling nice. And more to the point, they're feeling nice not to you. They don't care about you. They're feeling nice to the math professors using the book. Because after all, if you use Pythagorean triples, math teachers don't have to look at answers that look like 57.38437. They get nice numbers. So in this case, they were feeling nice to me, which I appreciate. Not very much, though. I really kind of like horrible answers. So that's 1 over, from the calculator, 85 feet. Up in the numerator, we have 51 times 68, which is 3,468 feet squared per second. Plus, sorry, 51 times 17. I'm losing my mind. I can't read my own writing. 51, cross that out. Let's try that again. Draw a nice line through it. 1 over 85 feet. And then the numerator we have 51 times 17, which is 867. That's square feet per second still, plus 68 square feet per second. So what's that? So add 68 to that. We have 935 divided by 85. And our answer is 11. At that very moment, and just defeat the denominator, cancel with one of the feet in the numerator in each term, so we end up with feet per second, which is what we expect. And the answer is 11 feet per second. At that 3 seconds later, after the moment they described, the bicycle is getting 11 feet per second further. The bicycle's distance from the balloon is increasing by 11 feet per second. Why is it slower than 17 feet per second? Because some of that distance, some of that speed that the bicyclist is doing isn't helping. Some of it, if you've done some vector math, the bicycle's trying to get away at 17 feet per second. He's scared of the balloon for some reason. And you could break that down into 2 components. There's a component that's at right angles to the line connecting the balloon and the bicycle. And that component is not helping him. He's not making him get further away. And another component that goes along that distance, and that's the actual rate at which he's getting away. And what we just learned is that's 11 feet per second at that moment. Well, it's not 11 feet per second. It's a little bit less than that because the balloon is also moving away. And we take into account all these different things. This is Nighttime Mathematics Radio. If you have any questions, feel free to tweet them in, and we'll try to answer them live here on the air. Okay, everybody, it's looking like a quiet night, so I think we're time to pack this in. If you have any math questions, feel free to keep tweeting them to @NightMathRadio on Twitter. I'll try to answer them right here live on the air. For now, in a world where the math homework goes on and on, but the math classes aren't meeting, stay safe, tweet your questions in, and I'll see you all tomorrow night here at Nighttime Mathematics Radio. Good night, everybody.